The giant planets are the dominant players of our solar system, second only to our sun. And yet, for as much as we know about some of these worlds, there's still much left to be discovered. But first, let's take a quick recap of some of the differences between the terrestrials and giant planets. Giant planets are much farther away from the sun than the terrestrial planets. Therefore, they're going to get a lot less solar energy. They're certainly much more massive than the terrestrial planets, and they're, of course, much larger. Now, the main difference, though, between giants and terrestrial planets are their very nature, in the sense that there are no surfaces, no solid surfaces that you can walk around. Everything that we see in the giant planets are really just their cloud tops, but those clouds continue all the way down until maybe just reaching a rocky core. If there is one, we're still not 100% certain yet, but there are no solid surfaces that you could walk around as you can do on the terrestrial planets. As we saw in a previous video, the giant planets formed farther away from the sun, and they had access to both refractory and volatile materials, whereas the terrestrial planets only had access to refractory materials, hence their relatively low mass and rocky composition. And giant planets have shorter rotation periods. The shortest rotating terrestrial planet is Earth at just 24 hours. Uranus is the longest rotator at just 17 hours. Now, because they are farther away from the sun, giant planets get much less sunlight than we receive here at Earth. Remember, brightness falls off as 1 over the distance squared. That means at 5.2 astronomical units, Jupiter is getting just 4/100ths the amount of sunlight we receive on Earth. Saturn at just 1/100th the sunlight, Uranus at 3/1000ths, and Neptune at just 1/1000th the sunlight that we get here on Earth. And the differences don't just stop there. The masses of the planets are much greater than we have on Earth. Jupiter is more massive than all of the giant, and in fact, all of the giant plus the terrestrial planets plus their moons combined. And the radius of the planets vary, but they're all much larger than Earth, with Neptune at just under 4 times the radius of Earth. The densities of these worlds are also very low. As a matter of fact, Saturn's density is less than 1 gram per cubic centimeter. In other words, Saturn will float in water, assuming you can find a bathtub large enough to accommodate it. The surface gravities of these planets do tend to vary. Now, at Jupiter, you would weigh a little bit more than twice your weight here on Earth. Now, you notice that Jupiter's mass is 318 times more massive than Earth, and yet its surface gravity is just 2.4 times the gravity that you would feel at the surface of Earth. So why wouldn't you weigh more? Remember that your weight is proportional to the planet's mass and the radius you are from the planet's center. So, on the one hand, Jupiter is a very massive planet, but on the other hand, it's a very large planet. So if you were, let's say, floating around in a dirigible in the clouds of Jupiter, and you were standing on a platform, you'd find that you only weigh 2.4 times your weight on Earth. But if you were floating in the clouds of Saturn, Uranus, and Neptune, you would weigh pretty much what you weigh here on Earth, so you'd be relatively comfortable. Now, the rotation periods of these planets are also very short. Jupiter's day is just under 10 hours, for example, and their obliquities, or their axial tilts, are kind of all over the place. Saturn and Neptune's axes are tilted at roughly the same angle as Earth's, but Jupiter has very little axial tilt to speak of, and Uranus has an extreme axial tilt, as if though it were essentially knocked on its side. So what does this mean for the seasons on these planets? Well, in the case of Jupiter, not very much. Jupiter's axial tilt is only 3 degrees. Therefore, it's getting roughly the same even amount of lighting in both its northern and southern hemispheres. So there's little, if any, seasonal variations to speak of. You could think of it as essentially springtime on Jupiter, all Jupiter year-round. But Uranus, on the other hand, is knocked over on its side. And it has an extreme obliquity, and because it has a very long orbital period, this gives rise to some very long and very extreme seasons. So in 1986, when Voyager 2 was passing by. It was summer in Uranus's northern hemisphere, winter in its southern hemisphere. But by 2007, spring had come to Uranus, and now we have even lighting in both of its hemispheres. But by 2028, the entire northern hemisphere of Uranus will be in complete darkness as its summer hemisphere begins its summer. So that means that Uranus's North Pole spent 42 years of continuous daylight, while its South Pole spent 42 years in darkness. I mean, talk about the phrase winter is coming. If you live on Uranus, you're going to experience a very long, very dark winter. Now, because these planets have such short rotation periods, their centrifugal forces kind of stretch them out into ellipsoidal shapes, so they get these oblate appearances, particularly Jupiter and Saturn, because their rotation periods are a little bit shorter than Uranus and Neptune's. Now, remember, we also categorize these planets based on their compositions. So Jupiter and Saturn are called gas giants, while Uranus and Neptune are referred to as ice giants. So let's compare their compositions very briefly. First, we're going to start with the gas giants. They're both basically composed of the exact same thing. They have hydrogen atmospheres, followed by a layer of liquid hydrogen. A layer of liquid helium rains down onto a layer of highly compressed hydrogen. And this hydrogen is under such tremendous pressure, about 100 million times the surface pressure on Earth, that the hydrogen can conduct electricity as though it were a metal. So we call this layer metallic hydrogen. Planetary scientists believe that there may be a layer of ices, of highly compressed liquid ammonia, water, and hydrogen ices surrounding Saturn's core, but the inner cores of the planets are still very much a mystery. We don't really know what lies at the very centers of these worlds. At these pressures, they may solidify into something, or they may be a collection of rocks and ices. It's still an open question. Now let's take a look at the ice giants. Uranus and Neptune are essentially twin planets. There's virtually little difference between these two worlds. Both have ammonia cloud layers, followed by an atmosphere of largely molecular hydrogen, and then underneath that is an ocean of water, methane, and ammonia ices. Now, this is not to say a layer of solid ice, but rather it's an ocean of mostly liquid water and methane and ammonia, and there may be some regions where it gets cold enough to become slushy and even icy in some areas. Whether or not there are rocky cores at the center of these planets, again, is an open question. We're not really sure. So the main difference between the gas giants and the ice giants is what they are made of. Gas giants are hydrogen and helium mostly, and they're really very much in the same proportion of hydrogen and helium as our sun. So you can think of the gas giants as kind of mini suns that never switched on. But the ice giants, well, yes, they are mostly hydrogen and some helium, but they're really dominated by water, methane, ammonia, hydrocarbons, all of those really highly volatile materials that require very cold temperatures to condense. We mentioned before how the giant planets are getting much less sunlight than the terrestrial planets do. However, they are much warmer than they should be. So when you compare the theoretical temperatures of these planets in blue to the actual temperatures, which are shown in green, you find that Jupiter, Saturn, and Neptune are considerably warmer than they should be. And the reason for this is because they are all warmed by internal heat, with the exception of Uranus, which doesn't seem to have any internal heat to speak of. So the sources of this internal heat vary from one planet to the next. Now, Jupiter is shrinking by about 2 centimeters per year. Now, that doesn't seem like a whole lot, but remember, Jupiter is very, very big. That means that there's still a lot of material that is contracting, and as this stuff contracts, it releases energy. In other words, it builds heat up, and this is what's believed to be the primary driver of Jupiter's heat. Likewise, Saturn is releasing heat at a rate of about twice that which it receives from the Sun. And this is believed to be a combination of gravitational contraction, primordial heat left over, but also the fact that Saturn is still differentiating. We talked about some of that helium rain, for example, and what we believe is going on is that there are still some heavy or rather dense materials that are still sinking into Saturn's core all this time later and releasing heat in the process. Now, Uranus is essentially in thermal equilibrium from the Sun, but Neptune, on the other hand, is perhaps the biggest surprise of the outer solar system. It radiates 2.6 times the amount of energy it gets from the Sun, and we don't know why. It is a mystery waiting to be resolved. Now, Jupiter and Saturn's magnetic fields are very powerful. In fact, Jupiter's magnetic field is the most powerful of any planet in the solar system, and both Saturn and Jupiter's fields are more or less aligned with their rotation axes. Now, Uranus and Neptune's magnetic fields are really weird. They're both tilted significantly from their rotational axes, and yet, stranger than that, they are also knocked off axis. They're knocked off the centers of the planets. So they're lopsided magnetic fields, and we really don't yet understand why. But this tells us that there's something fundamentally different about the way the magnetic fields operates in the ice giants than they do in the gas giants. In fact, we could take a quick visualization of the magnetic field. So if we have these yellow arrows facing the Sun and the magnetic axis represented in cyan, you could see that Jupiter and Saturn's fields are pretty much co-rotational with their rotation axes, kind of what you expect and really just enlarged versions of the magnetic fields that we have here on Earth. But when we get to Uranus and Neptune's fields, yeah, they're just really off axis and also off center. So again, this is something fundamentally weird about these two worlds. Now, Jupiter's magnetic field is the largest and strongest of any object in the solar system except for the Sun. And this magnetic field is buffeted by the solar wind, so it creates this massive magnetosphere that surrounds Jupiter and extends far out into deep space. In fact, it could easily extend out to the orbit of Saturn and probably goes even farther. And it's interesting to think about because if we could somehow see Jupiter in magnetovision from Earth, we would find it's enormous. It would be a little bit longer than the diameter of the full moon. So it's an extremely powerful magnetic field. And Jupiter's magnetic field is the source of spectacular aurorae, especially when viewed at ultraviolet. And here's a movie of Saturn taken in ultraviolet light. And if you look along the northern and southern polar regions, you can see the lights caused by charged particles from the Sun funneling into the magnetic field lines and reacting with gases in Saturn's atmosphere. And we've even captured aurorae on Uranus. Now remember, Uranus's magnetic axis is off-center. It's lopsided and off-center, and sure enough, the aurorae are occurring kind of away from the rotation axis of Uranus. Let's talk about the atmospheres of these worlds. Now, Jupiter and Saturn essentially have the same compositions. They're both made of primarily hydrogen and some helium. And yet Jupiter has these beautiful, vibrant clouds and bands, whereas Saturn's are more muted. They're a little less spectacular. So what accounts for the difference? Well, these atmospheres are largely composed of the same things, namely ammonia and ammonium hydrosulfide and water ice cloud layers. But if you notice, these layers on Jupiter are kind of packed a little bit tightly together, almost like one on top of one another, like a kind of a cloud layer sandwich. Whereas on Saturn, these layers are spread out over a much wider altitude range. So that tells us that Saturn's atmosphere is much less dense than Jupiter's. The cloud layers just don't stack up, allowing us to see them very easily. And not only that, but the cloud layers on Saturn form at much lower altitudes. So we have to see through more of that upper haze layer before we can start to see the cloud layers in Saturn. So it's not that the chemical compositions are fundamentally different, but these cloud layers rather are arranged a little bit differently. Because of the low density and because of the lower atmospheres at which they form, we really don't get to see very much in the way of Saturn's cloud layers. But this doesn't mean that Saturn lacks any features that are interesting. I mean, take a look at this. This is a magnificent image of Saturn's polar region. There's this hexagonal jet stream that flows around Saturn's polar caps, much like the jet stream on Earth does as well, except it's at a much larger scale. Now, Uranus and Neptune's are kind of featureless by comparison. Remember, Uranus lacks any internal heat, so there really isn't any convection. And so this gives Uranus a very clean, stable atmosphere. But Neptune, on the other hand, has internal heat, so there is some convection. And we do get to see some atmospheric features, albeit not as dramatic as some of the ones that we see on Jupiter and even on Saturn. So let's take a look at their atmospheric compositions. Well, the planets are essentially twins of one another, and they have essentially the same atmospheric composition, namely methane and diphosphane cloud layers, with a haze layer of largely hydrocarbon ices, methane and ammonia ices in the atmospheres. And it's these hydrocarbons that give these planets their characteristic blue aqua colors. Essentially, they absorb red light and scatter blue light everywhere. Now, the wind and weather of Jupiter in particular is the most spectacular of any planet that you're going to see in the solar system. I mean, it just kind of looks like a mesmerizing kaleidoscope of vortexes and swirls and bands and winds and just all kinds of complex weather patterns. This image was taken by the Juno spacecraft. It's a spacecraft that's orbiting very close to Jupiter, allowing us to get these really nice detailed images. And when we enhance these images to really bring out different details, you can just see how complex this stuff really gets. And Jupiter's short rotation and heat convection give rise to these dramatic east-west zonal winds. So this is all due to the rotation and convection. And remember, there's no surface on any of these planets for the winds to kind of lose energy against. So they just keep going and going, particularly on Jupiter, which is rotating so rapidly. In fact, if you take a look at the speeds themselves as a function of latitude, you can see where they are blowing the fastest, which is largely around the equatorial regions. But as you get up into the polar regions, the wind speed variations aren't nearly as dramatic. Now let's scale this down and compare that to Saturn. Despite the fact that Saturn doesn't seem to be as active a planet as Jupiter, it boasts some of the fastest winds in the solar system around its equatorial region. By comparison, Uranus's winds are very stable. So because of a lack of convection, there is generally a lack of wind variation. They're essentially symmetrical around the poles. But Neptune, once again, was the big surprise. Its winds were clocked as supersonic. I mean, these were just the most powerful winds detected anywhere in the solar system. And keep in mind that Neptune's just getting 1/1000th the sunlight that we get here on Earth. So Neptune's got an energy source that's driving some of the most spectacular weather anywhere in the solar system. And that weather manifests itself in storms. So these storms, such as Jupiter's Great Red Spot, are essentially high-pressure regions. And that's very different than the kind of storm that we get here on Earth, which are mostly low-pressure regions. And these storms are going to be fed by the convection and the rotation. And remember, there's no land, and so these storms can rage for a very long time. And in fact, Jupiter's Great Red Spot has been visible to astronomers ever since telescopes were first used. So that means that at a minimum, the storm has been going for about 200 years, but some estimates suggest it may have been around for as much as 500 years at least. And this is the largest storm in the solar system. In fact, once upon a time, it was 3 times the size of Earth. But over time, it shrank, and now it's just only a little bit larger than Earth. So the Great Red Spot is shrinking, and it's getting less oval. It's becoming more circular. And we don't yet understand what the fate of the Great Red Spot will be. Will it continue to shrink until it finally dissipates? Or will it reach some kind of equilibrium and stabilize? It's something that we are still trying to figure out. Now, the Great Red Spot is also apparently a source of heat. In other words, it's kind of like a gaping region where heat from the interior of Jupiter can escape. And this is why Jupiter's atmosphere is even hotter than it otherwise should be. So the Great Red Spot seems to be a source of heat, and maybe there's a relationship between the amount of heat it's releasing and its contraction. But storms like the Great Red Spot aren't just limited to Jupiter. Saturn itself has been known to display its fair share of storms, and in 2010, the Cassini spacecraft, which was at the time orbiting Saturn, noticed a storm breaking out in its northern hemisphere. And the storm got larger and larger and began to spread eastward and eventually wrap itself around the entire planet. So these storms can sometimes become planet engulfing phenomena. In 1986, Voyager 2 flew past Uranus and didn't really see much of anything going on. 3 years later, it passed by Neptune and found some spectacular weather. So for a while, we thought that maybe Uranus was always going to be a featureless world. But as Uranus approached its equinox, its southern hemisphere began to wake up, and with it, some stormy weather. These storms that you see are about the size of the continental United States. So it's possible that Uranus is just as active and just as magnificent as Neptune. We just caught it at the wrong time when we flew past in 1986. Now, Neptune, on the other hand, had the fastest winds ever detected. So this was a real surprise considering that there is such little sunlight reaching this planet. And we even found a great dark spot in Neptune's southern hemisphere. However, by 1994, that dark spot had already disappeared. And then by 2016, a new dark spot reappeared. So Neptune's still undergoing some really interesting weather changes that we're still trying to understand. We know a lot about Jupiter and Saturn, but very little about Uranus and Neptune. And it would be great to get some spacecraft out there someday if we are willing to do that. But there's something really amazing about these worlds still waiting to be discovered.